Let's improve our understanding of how transitions of the electrons in the atom give emission spectra. We observe emission spectra when we heat gases and pass their emitted light through a prism or diffraction grating. Then we can see the spectrum. Now, hot gases emit light. If we fill a tube like the one on the right with a gas like hydrogen or neon, we get an emission tube that we can then heat to produce light. You'll note the two electrodes on the two ends that will fit into a device that will heat them. An easy way to heat a gas is to subject the tube to a very high voltage discharge. The atoms will then absorb energy and emit light, as you see here. Hydrogen gas, when heated, emits light in a unique combination of wavelengths. A spectrograph, then, when you point it at the tube as it is emitting light, will separate the various wavelengths, and you can see the wavelengths here for the hydrogen emission. Now, this spectrum shows only the lines visible to our retina and brain. There are also lines on the left and the right of the ones you see here, and we'll see that complete spectrum later on in this slide series. Niels Bohr postulated that electrons emit light in this way because they can only orbit at certain distances from the nucleus and therefore have particular energy levels. The farther away they are, the higher is the nuclear energy level of the electrons. Here we see diagrammed a change in electron energies from energy level 3 to energy level 1. You notice as the energy levels increase in number, they get closer together in delta E. The 3 to 1 change diagrammed here gives off light that our eye can't see. It's in the ultraviolet range. But when electrons drop from n equals 3 to n equal 2, though, the light is visible to our retinas as a red line. And so are the other drops that go to n equals 2. There's a light blue line, a darker blue line, and this is so violet it may be difficult for the eye to see. As the drops in energy get bigger, the wavelength then gets smaller, the energy increases, and we move into the ultraviolet range. That gives us more lines, as we'll see in a little while. The smallest energy drops, like 7 to 6, are going to give lines in the infrared range of the spectrum, which is to the left of the visible. So there is the set of infrared lines from hydrogen. The largest change in energy, and there's several of those as you can see, like 5 to 1, 4 to 1, 3 to 1, give light in the ultraviolet range. And so the farther to the right they are, the higher is the frequency, the lower is the wavelength. So electrons that are energized then into the third energy level have two ways to lose energy. They can lose it in 2 steps, or they can lose it all at once. So there we're seeing it move from 3 to 2 and then from 2 to 1, or a much shorter wavelength and higher energy would be the fall from 3 to 1. And you might want to take some time to diagram the possible changes from 4 down to 1 and from 5 down to 1. If it's hydrogen, it's always going to go back to its ground state of n equals 1. Now, we can look beyond hydrogen just for a moment. The visible portion of the emission spectrum of element 2, helium, is shown above. You'll note the additional lines. These lines are characteristic of helium, and in fact, late in the 19th century, when the spectroscopy was tuned to the sun, they saw these lines as absorbance lines in the solar spectrum, and they realized they discovered a new element that they then said was in the sun. And they called it helium after Helios, the Greek word for the sun. And later on, they were discovered on Earth, particularly in natural gas wells, which made Texas a very big part of the helium generation scene. It's now produced in other parts of the world. The visible portion of the emission spectrum of element 80, the spectra of mercury, is now shown here. So note the additional lines that we see, more than helium, more than hydrogen. It's also interesting to see the pairing here at 577 and 579 nanometers, suggesting that it's a very, very close drop in energies. The Bohr model, to explain complex atoms like the ones we just looked at, has to be modified, and it's been modified into our modern quantum atom with the various types of orbitals, not orbits. And it was largely because the Bohr model could not predict the emission wavelengths from atoms with more than one electron. Let's just briefly see on a very, very basic level how that might be. If you add that second electron, you can easily see that an electron that has been energized from 1 up to 3 may still have the second electron in the first energy level. What that does is it partially shields the electron that's been energized, that's been activated, jumps to third energy level. It partially shields it from the nuclear charge, and therefore the energies of the various levels will change because of that shielding effect. Moreover, when we look at the quantum atom, which we now use, we see that there are many sublevels of atomic structure that can add to the possible number of energy changes, and therefore the number of wavelengths and their value in terms of nanometers that would be emitted by those atoms. And so we can see here we've diagrammed the various sublevels of the second and third and fourth and fifth energy levels for you to look at and see, well, there's a whole lot more changes here. In fact, our 4 orbital classes, SPDF, come from the character of the emission spectra, the lines that we see in many spectra of heated elements beyond hydrogen. And the lines for each class of orbital were named sharp, S, principal, P, diffuse, D, and fundamental, F. We're not going to get into that in this very short video. You can continue your study in a course in atomic physics.